conditional probability and PDF. The conditional probability of an event A given another event B, denoted as PA given B, is defined as the ratio of the probability of the joint occurrence, PA and B, and probability of B. For independent events, clearly the above becomes the unconditional probability, because then PA and B is the product of PA and B, and therefore PB cancels, and by the way, PB has to be non-zero for this to make sense, and you end up with PA. Independent events, if you try to condition one on another, obviously it should make no difference. Similarly, the conditional PDF of one random variable given another random variable is, using the simple notation that we introduced earlier, is P of x given y is P of x and y divided by Py. For an event conditioned on a random variable, P of the event A conditioned on x, this is equal to the joint probability PDF of the event A and the random variable x, using this notation with the brackets introduced earlier, divided by the PDF of x. The conditional PDF of a random variable x given an event A, that's the other way around, PDF P of x given A is P of A and x divided by P of A, where again we use this mixed probability PDF defined earlier. Let's take an example. Consider the conditioning event A as the fact that the event that x is less or equal to the number lowercase a. What we get with this is, as you will see, is a truncated density, truncated PDF. That's a P of x given x less or equal to a is probability of the random variable x and the fact that it is less or equal to a divided by the probability that it is less or equal to a. This turns out to be the PDF of x divided by the probability that x is less or equal to a if x is less or equal to a. And this is from the following fact that the event x less or equal to a is automatically satisfied when x is less or equal to a. Therefore, I end up only with the PDF of x, so just the first is relevant. If this is not so, namely x is greater than a, obviously this requirement makes the numerator equal to 0, therefore I end up with 0. So we end up with the PDF as before, limited or truncated at a and renormalized suitably such that again it integrates to 1. So it's shorter but higher. So it's the original one restricted to x less or equal to a and renormalized for area 1. Now, if I take a random variable z defined as the sum of x and y, then the conditional PDF of y given x will be denoted by P of y given x with the argument here. With this, we have the following result. The P of z given x is the same as P of y given x evaluated at z minus x. Clearly, if x is a constant, what we have is a given value of x. Therefore, the only random component now is y, but I have fixed x, therefore the behavior of y is according to this density. So what we have is the probability description is according to the py given x, but the argument will be this, because y is z minus x, this is my argument. So it's a shifted version of z. So PDF of z is really the py given x at z minus x. Now, if x and y are independent, that will have an implication on this. What we have is, with py denoting the PDF of y, p of z given x is just plain p sub y at z minus x, and here we do need the full notation with a subscript on the function to know which function we are talking about, because we talk about one function, the argument is something a little bit different than its original argument. Now, if x is Gaussian, would mean mu sub x variance sigma x squared, y also Gaussian would mean mu sub y variance sigma y squared, and these two random variables x and y are independent. With z being the sum x plus y, the PDF of z given x, because of the independence, is just a simple p sub y at z minus x. Now, what is p sub y? We know p sub y from here. The argument is z minus x. Here's the argument. Here are the two parameters, mu sub y, sigma y squared, which I can write now with the explicit form of the Gaussian density. Here's my argument, z minus x minus the mean squared over twice the variance, with a minus here in the exponent, and the variance is just sigma y. That's the same sigma y that we have here. Now, what I can do is change the way I look at this density and say I'm interested in z. Therefore, I can lump this constant x, remember x is given, conditional is a constant right now, into the mu sub y. So I can shift and say this is Gaussian with now the argument z, x plus mu sub y, and the variance still sigma y squared. So because of this special form, we can switch our view of the density, and we end up that this Gaussian is really the same as this Gaussian. Therefore, pz given x is Gaussian with argument x, and x adds Gaussian with argument z, and x just adds to the mean mu y. Now, if x is Gaussian with mean mu and variance sigma square, we can write the PDF of x given that x minus mu in magnitude is less or equal to the number a, would be a truncated version of this original Gaussian density, which is written out in full as n argument x mean mu variance sigma square, as long as x is in magnitude less. This should be x minus mu less than a, not x minus mu less than a, and divided by the probability of x minus mu less or equal to a, such that again this truncated version of my original Gaussian density, I truncate both on the left and on the right now because of this. Again, that's magnitude x minus mu less or equal to a. So the integral of this twice truncated once on each end, PDF would be again equal to unity. So that's a simple truncated Gaussian. Now, the normalization constant above is the probability that x minus mu lies in that closed interval minus a to plus a. So either magnitude x minus mu less or equal to a, the probability of this event can be written in another fashion as follows, is x minus mu is an element of the interval minus a to plus a, or x is a point inside the interval between mu minus a and mu plus a. You can easily see that this is just a shift of my interval. Therefore, I can write it now as being in this interval, mu minus a to mu plus a, as the probability of x in the minus infinity interval, all the way from the left up to mu plus a, minus the probability of the event that x is outside my interval, which is between minus infinity and the left end of my interval, that's mu minus a. So I just add a semi-infinite interval to it and then take away the same one. Now, what this allows us is to write each of these using the cumulative standard Gaussian distribution, script cap G, with element being mu plus a here. The mean, it is because the mean of x is mu, I have to subtract it, and this is the upper limit of my interval. Same thing now, the upper limit is mu minus a, I subtract the mean of the density, divide by the sigma, the standard deviation, because this is the essence of the Gaussian, the standard Gaussian density. It has mean 0, so I've got to subtract the mean, and variance 1, so I've got to divide by the standard deviation. And this is Gaussian at a over sigma, the Gaussian distribution, minus at minus a over sigma, or 1 minus twice at minus a over sigma, because of the symmetry of the Gaussian around 0. The Gaussian distribution in this case is, you just take off twice this. That's a tail. Now, so these are the tail probabilities to the left of minus a over sigma and to the right of plus a over sigma. Another important result is the total probability theorem. If we have a set of events bi from I going from 1 to n, mutually exclusive, namely their intersection has 0 probability, the joint probability of any pair bi, bj for I different than j is 0, and these events are exhaustive, namely the sum of the probabilities of bi is unity, that's a sure event. Bi really form a partition of the space of outcomes. Such a set of events is a partition of the space of outcomes. Then, the so-called total probability theorem states that for any event A, its probability can be decomposed in terms of conditional probabilities as follows. P of A is sum of the probabilities of the intersections of the events A and A with each of the BIs. And the reason this works is because of the partition of the space into all these BIs. And now using the definition of the conditional probability, I can rewrite P of A and BI as P of A given BI times PBI. That's just a simple algebraic reshuffle of the definition of the conditional probability. So the key to the above is the mutual exclusiveness and exhaustiveness of the set of events BI from I1 to n. And here's a graphical representation of this, or illustration, with a set theory counterpart. Take a set A, intersect it with the bunch of BIs. Each BI, you consider the entire space is divided in this case into 4 BIs, and I take the union of each such intersection, A with B1, A with B2, this small rectangle, and this, and this, and this, and their union gives me back the event A. So the mutual exclusivity means I never count twice, and the exhaustivity, I count all the portions of A. The version of the total probability theorem for random variables is you take the joint density of x and y, integrate out over y, and you end up with the marginal of px. And this really is completely equivalent to what we have seen for the case of events, namely integral of p of x given y py dy being the same as pxy is p of x. So this is really a combination of the definition of the conditional PDF and the property that the joint PDF integrated out with respect to one of the random variables yields the marginal of the other random variable. And here we say the joint PDF of two random variables. If we have a mixed event random variable situation, the marginal density of just the PDF of x can be written as the sum of the PDF of x given a BI times the probability of that BI, where the sum is over all the BIs, again mutually exclusive and exhaustive, and this recreates the original density. And we'll see an illustration of this later. And the other way around, the probability of the event A can be written as the integral of the probability of the event A conditional on the random variable x times the PDF of this random variable x dx, which can be written, if you remember the definition of the expectation, this is nothing but the expected value of this function of a random variable s. P of A given x is a function of the random variable x. Therefore, what we have here is the expected value of the probability of the event A given x over x gives us the probability of A. Okay, let's look at some examples. We take the event A as success in hunting or target shooting if you want, and this can be modeled as a function of the miss distance x by a conditional probability. P of A, that's success in hunting, target shooting given x is 1 if x less or equal to d1, namely your miss distance is below some threshold. It can be written, in this case, assumed to be linearly going down from 1 to 0 as x goes from d1 to d2, and if x is greater than d2, it is 0. So this miss distance PDF can be taken, we'll use an expression here, P of x is, this is a triangular density, we'll see it in a moment. So between 0 and A, there's some value highest at 0, lowest at A, at which point it becomes 0 and it stays 0 after A. So what we have here is a miss distance triangular probability density function. Remember, miss distance has to be positive because it's a distance. And here is the probability of the event A given the miss distance. 1 goes down to 0 at D2, then it stays 0. Now, assuming D2 less than A, the unconditional probability of success is P of A is integral P of A given x px dx. And this is the integral of the miss distance from 0 to d1. That's where the probability of the event A is unity. Here it is less than 1, and we integrate with respect to px. After d2 it is 0. Therefore, what we have is the third term is 0 and it doesn't even appear anymore. This gives us the first integral, just the probability of x less or equal to d1. The second, we have to carry out an integral, and we get some expression here. And the probability of x less or equal to d1 is the part of that, the area of the triangular distribution up to point d1 can be written here. And this is what we have now as the second one, with the probability of success in hunting goes towards 0. So we have an expression now for the unconditional, the overall probability over all the possible miss distances given that particular triangular PDF of the miss distance and the particular probability of success in hunting given by that function that starts at 1, goes down in a straight line to 0, then it is 0 as a function of the missed distance. Bayes formula is another very important tool which allows us to switch conditionings. Namely, if I'm interested in the probability of some event bi conditioned on A, I can write it as equal to the product of probability of A given bi times the unconditional probability of bi divided by the probability of the event A. And you can very easily see that this formula, which is known as Bayes formula or Bayes theorem or Bayes rule, some of these terms are not quite rigorous, but it doesn't matter much, follows from the fact that P of A times PBI given A is the joint probability of BI and A, and here we have the joint probability of A and BI, but this is a logical AND. The order doesn't matter, therefore the two sides are clearly equal. The conditional probability of BI is sometimes referred to as a posterior probability, while the unconditional one is referred to as a prior probability. And the reason for this is typically we have prior to making an observation, the unconditional probability after we make an observation or gather some information, we have a conditional probability based on that information we just obtained. Using the total probability theorem, for the denominator in the Bayes formula, would Bj, j from 1 to n mutually exclusive and exhaustive, we can write P of Bi given A as Pa Bi times Bi, and the denominator, which was a P of A, is expressed as a sum j from 1 to n Pa given Bj, Pbj with a different dummy summation index here. But if you look at what the denominator is, it is nothing but the sum of all the possible numerators. So the denominator C appears as being nothing but a normalizing constant, which guarantees that if you sum over all the I, 1 from n, the PBI given A, you get 1. So this is clearly a normalizing a normalization constant here. Now, for random variables, we have a counterpart for Bayes formula, very similar to what we had for events. P of x given y is P of y given x px over py. And leaving the numerator unchanged, we can use the total probability theorem or the fact that the marginal of y is really obtained from integrating the joint of x and y over all the possible values of x. We have the second expression for the denominator. Again, we have a prior PDF term of this unconditional one. The conditional one is called posterior PDF, so this is px, y is posterior, or after we get the information y, p of x is what we have about x, the knowledge about x, before we get the extra piece of information y. And we have similar results for the mixed case. P of bi given the random variable x is PDF of x given bi times pbi over px. And again, the rule is exactly the same, the explanation of Bayes formula or the proof, and with the denominator written as sum j from 1 to n p of x bj pbj, we can see that what we have in the denominator is the normalizing factor, because that's exactly all the possible numerators. And we use on purpose an I here and a dummy index j there, which takes the same values, but j is a running index. Few remarks. Now, what is the prior? It turns out that, especially in engineering systems, a prior could reflect a possibly subjective initial degree of belief, which when combined with the evidence from data, as we'll see, this is called the likelihood function of x, is the PDF of y given x. We have not seen this term yet, but we'll see it quite often later, yields the posterior. So you have a prior Sometimes you make it up subjectively based on what you believe, based on physical evidence, based on the physics of the problem, and you end up with a posterior about x after you make the observation y. Now, Bayes' postulate states that in the absence of prior knowledge, we should use a uniform prior PDF. This is reasonable for discrete valid random variables. For continued valid random variables, this would imply a non-uniform PDF on, say, you have a prior on x uniform, on x squared, it turns out it is not uniform. So, there is some controversy among statisticians, but I don't believe it is of much consequence for us. Now, there's another interesting thing, is the use of a uniform prior PDF over an infinite interval called diffuse or non-informative. Uniform, the value of the PDF is 1 over the length of the interval. Now, what happens if the interval goes to infinity? The PDF goes to 0, but what is the integral of 0 from minus to plus infinity? Not clear whether it is 1. So what we do typically is keep the limits large, not quite infinite. That's called large enough. And we have what is called the Dirichlet prior, and we'll come back to it later in the context of parameter estimation. It's a very useful tool because it allows unifying several concepts which appear different, but really they can be presented as a single tool in probability theory. Some examples. The noise in a device, that we denote this noise by x and model it as a random variable, is observed. Assuming we have a device operating according to its standard specifications, then you have event B, defined as B1 is the event that x is normally distributed with mean 0 and variance sigma 1 square. Now, if the device becomes defective, effectively what you have is much more noise. Every perfect or well-operating device will have some noise, hopefully low noise. A device that's not working properly has a large noise. So what we have is somewhat simple definition of a defective device, that the noise in it is still Gaussian, still means 0, but a new variance sigma 2 square. Now, what we're interested in, we make, say, one observation of the noise, and we would like to infer from that single observation whether the device is operating according to specs or not. What do we have? The probability of the event B2, defective, given the observation, a single observation x, will be the probability of x given B2 times the prior probability of B2, divided by the normalization constant, which is written out as a sum of two terms because we have two B's. B1 is device operating according to specs, B2 defective. So what we have is, after a slight reworking of these expressions, PB2 given x, there's a division of the Gaussian with variance sigma 2 squared that would come here. So we get a simpler expression. And what we have here right now is 1 over 1 plus. This is the ratio of the two PDFs, P of x given B1. This is P of x coming from P of x given B2. Change has been sign has been changed because it was negative exponential of a negative quantity, but in the denominator. And this came from the numerator that was brought down here, times PB1 over PB2. So you have here the prior probabilities. Now, assuming we don't know what is the prior probability of the device being okay or defective, take each of them half. and assume that the defective device exhibits a standard deviation of the noise 4 times larger. The power of the noise is 16 times larger. The variance is 16 times bigger. And assume the observation that you get is, for the sake of example, x at sigma 2, like 1 sigma value of the large noise. The question is, what is the conditional probability that this device is defective? PB2 given x, using the expression we had before, turns out to be 0.998. Now, this is with a uniform prior, which means if you don't know a priori, up front, whether the device is defective or not, give the device half probability of being defective. Now, assume you know that the device can be defective with the prior probability of 10 to the minus 2. That's a lot smaller than the half in the previous case. What is the conditional probability of the device being defective given the same observation? It's still a high number, 0.82. So regardless of the prior, in this case, the evidence from the data, which is x equal to sigma 2, indicates a very high probability that the device is defective. What this says is one should not be afraid of making some assumptions, like a prior belief in the device being defective versus a posterior probability based on that and the evidence from the data. Now, Gaussian random variables, we've already seen them, but we'll formally define this. P of x is a Gaussian argument x, mean x bar, variance sigma square, 1 over square root of 2 pi times sigma, e to the minus x bar square over 2 sigma square. So this is the normal PDF, or Gaussian, with argument, mean, and variance. The first two moments which fully characterize a Gaussian random variable are in many cases referred as the statistics of the Gaussian random variable. The mean and the variance are colloquially referred as the statistics. Another equivalent notation is x distributed normally with mean and variance. So we have these two meanings of the script n. Once with 3 arguments is a function with 2 arguments distributed as, which provides the same information except it's not a function. Now, the more interesting thing is vector-valued Gaussian random variable will have a density. And again, we use exactly the same notation with the 3 arguments. X is the variable, x bar is the first moment, the mean vector now, this is a vector x, and P is the covariance matrix. So x bar is the expected value of x, P is the expected value of this column vector times this row vector. It's an n by n matrix, and without proof we give the result that this is a constant, normalization constant, e to the minus half, a quadratic form x minus x bar transpose P inverse times x minus x bar. Now, this is the determinant of the matrix P multiplied by 2 pi, and remember when the A matrix is multiplied by a scalar, if it's an n matrix, its determinant will have that scalar taken out or multiplying the determinant raised to the power equal to the dimension of the matrix. So instead of saying what's the dimension of the matrix, it's more convenient to keep it inside here. The components of a Gaussian distributed vector are jointly Gaussian. So really a bunch of jointly Gaussian random variables, if you put them into vector, give you a Gaussian vector, that's all. Now, if the covariance matrix P is diagonal, then the components of the Gaussian random vector are uncorrelated, In this case, they are also independent because their joint PDF equals the product of the marginals. And this comes from the fact that when the covariance matrix P was defined, its diagonal terms are variances and the off-diagonal terms are covariances. And this is the reason why in some statistics texts, what we call in engineering a covariance matrix is called by statisticians a variance covariance matrix. Again, diagonal terms are variances, off-diagonal terms are covariances. We just call it covariance matrix and understand with this simpler designation the same thing. Now, if the matrix is diagonal, means all the off-diagonal terms are zero, therefore all the covariances are zero, and this follows from the fact that if you have the Gaussian density, the joint Gaussian density breaks down into the product of margins. That quadratic form in the exponent of the Gaussian density for that random vector becomes the sum of, from the quadratic form you end up only with the diagonal terms contributing, therefore you end up with the sum of the xi square over 2 sigma I square, and the exponential of that sum is the product of the exponential, so immediately the joint density breaks down into the product of the marginal density. So you have the independence property. The joint PDF equals the product of the marginals. A very important property of Gaussian random variables is that they stay Gaussian under linear transformations. The sum of two Gaussians is Gaussian. You multiply, take any linear combination, Gaussian times a constant times another, plus another Gaussian times another constant, again Gaussian. This is a major reason that the Gaussian model is very commonly used in estimation. Namely, what we have is linear system, the tools from linear system theory combined with the results from Gaussian random variables provide us very powerful results. Let's take an example. x1 and x2 are random vectors of the same dimension and jointly Gaussian. P of the combined vector, stacked vector consisting of x1 and x2 will be also Gaussian. So this is a vector of double dimension. The argument is this vector. The mean is the same stacked vector of the means x1 bar and x2 bar, and the covariance matrix is P11, that's a block, and P22, and the second diagonal block with off-diagonal blocks, P12 and P21. We'll see them immediately in more detail. Then, this is the covariance of x1 with x2. This is the transpose or the covariance of x2 with x1. Remember, when we talk about vectors and matrices, the order of multiplication matters, and you can switch. x1 times x2 transpose is the transpose of x2 times x1 transpose. So this is the reason that P12 and P21, these two matrices are one the transpose of the other. Now, we'll take x as the sum of these two vectors, x1 and x2. And the first result, this is Gaussian. Second, the mean of the resulting sum x bar and the covariance of the resulting x bar are given by the following. X bar is x1 bar plus x2 bar, and the covariance P of this sum is P11 plus P12 plus P21 plus P22. And this is obtained simply by multiplying this sum minus its mean with its transpose and taking the expected value. Now, if x1 and x2 are independent, then the off-diagonal blocks P1 to P21 are 0 because all the correlations between them are 0. What we are interested now is in PDF of x given one of them. So this is the PDF of x2 given evaluated at x minus x1. So the PDF of the sum x1 and x2, x1 plus x2, given that one of them is a fixed value, that's a constant, is a shifted version of the PDF of x2 by just that quantity x1. So this is Gaussian. Argument is x minus x1. Mean is x2 bar because that's a p sub x2. Covariance is p22. So we can write it as 2 pi p22 determinant to the power minus half, and the exponential of half this quadratic form, which is x minus x1 minus x2 bar. And again, as before, we can take this constant and lump it into the mean. Take it away from the argument, put it into the mean. So we end up with Gaussian. Now the argument is a plane x. The mean is x1 plus x2 bar, and the covariance is p22. But that's very simply seen from here by simple inspection, that if x is x1 plus x2, the PDF of x given x1 is just take whatever randomness you have about x2, add to it the constant x1. What the constant does, shifts the mean. Because it's constant, it does not have any impact on the variance, on the covariance matrix. That's why we still have the same p22 as before.